going to look at solving systems of linear equations. Actually, just a brief introduction. Suppose that you were told that dx dt is equal to 4x minus 7y, and dy dt is equal to 5x, which also means plus 0 y's. Now, as you can always add 0, and 0 times y is 0. Never ever be afraid to add 0, and never ever be afraid to multiply by 1. Okay. Now, we want to write this in matrix form. We want to write it as x prime is equal to some matrix times x, whereby x prime, bold x, so let me write prime. Vector, that's what the line above means. Vector or matrix x prime is equal to matrix A times matrix x bar. X bar is just little xy. It has nothing to do with that x. Some other matrix is x prime, y prime. That matrix happens to be called y bar prime. Or, excuse me, x prime with a bar on it. So, what we do is we say x prime, x prime bar, which rarely means little x prime, y prime, is equal to some matrix times x bar. That is some matrix times x. Well, if I put 4 and negative 7, 4 and negative 7, well, when you multiply, you're going to get 4x minus 7y. And that's supposed to equal to x prime, or dy dx. Exactly this. The other equation says that y prime is 5x plus 0y. If you multiply this second row by that column, you get 5x plus 0y, or 5x. And the second row equals y prime. So this is working nicely. The only thing is we should just call that x bar. So all I did was take the coefficients from here, x is first, y second, put them there, and over here, I was mathematically mature enough to add 0y, and I put the 5 and the 0 down here. Of course, if this would have just been 7y, we'd have to realize that 0x plus 7y, so I would put the 0 there and the 7 there. But it wasn't that, it was just 5x. So I wrote this system of equations in matrix form. Try another one. Suppose you came to know that dx dt is 31x minus 11y, and dy dt is 2x minus 4y. Well, then x bar, or x prime, is equal to the matrix 31, negative 11, x's and then y's. The second row, x's and then y's. The 2, the negative 4. And this gets multiplied by x bar. And this is exactly right, because the left column, the left side, x bar prime is just x prime y prime, and the right side, I suspect something's wrong here, like I clearly said, is 2 negative 4. So let me put a 2 there. And when you multiply this by x bar, which is xy, if you did this multiplication, you get 31 times x minus 11 times y, 2x minus 4y. And this equals that. Well, yeah, that's what it says. Remember, x bar is just y, it's just dx dt, and it equals to 31x minus 11y, and dy dt is equal to this, just like it said. So the answer, write that top system of equation in matrix form, there is your answer. Right, let's try another one. This one will be more difficult. It'll have x, y's, and z's, and t's for each derivative. Suppose that you come to learn that dx dt is 8x minus 3y plus e to the t cosine t. Dy dt is 2x minus 4z plus 3e to the t times the sine of t, and dz dt is, say, 2y plus 3z plus 2e to the t. What you should do is isolate the t's. And then, just like in the last problem, except here we have 3 variables, write this in matrix form. So x bar, x prime bar will be x prime, y prime, z prime. X bar prime has nothing to do with the variable x. And just x bar, well, that means little x, little y, little z. It doesn't have anything to do with x. So I want to write x prime is equal to some matrix times x. Well, the matrix, well, there are 3 columns. Column x, column y, column z. We have 8 x's, negative 3 y's, but no z's. That's x prime. Almost. We have to take care of this part in the end. Y prime is 2 x's, no z's, no y's, and minus 4 z's, plus this. We'll get to that in a moment. And then for dz dt, or z prime, we have no x's, we have 2 y's, 3 z's, and then more. Well, if we multiply this by x, y, z, that is x bar, we will have dx dt is equal to this, plus e to the t cosine t. And dy dt, which will be this times xyz. That is, you'll have this, plus 3e to the t sine t. When you dz dt will be this row times that column being xyz. And it's going to give you this. But let's not forget to add on 2e to the t. And there it is. There it is. Just take this and let me just erase one little thing. Just take that and add it on. There it is. So when you have t's, it's functions of t's, it's not a big deal. Just deal with this first, which will give you this, plus the t's. Don't let that bother you. Now let's reverse it. You want to write this without matrices. Suppose you come to learn that x bar prime is equal to 3, 1, 2, 4 times x bar plus 3, negative 2 times e to the 3t. Take as many steps as you need. This is 3, 1, 2, 4 times, while x bar really means little x, little y. Why does it mean little z as well? Because there's only 2 rows, or if you prefer, only 2 columns, column x, column y, plus 3, negative 2 e to the 3t. Okay, now remember that that really means x prime, y prime equals this row times that column is 3x plus y. Don't forget to add on 3e to the 3t. And this row times that column is 2x plus 4y. And don't forget to add on negative 2e to the 3t. I'd only give you 90% credit here. You really should write, because this is matrices. Maybe the right side is not a matrix, but the left side is surely a matrix. X prime, or dy dt, is 3x plus y plus 3e to the 3t, and dy dt is 2x plus 4y minus 2e to the 3t. You can write this, or you can write dx dt. You can write that, or you could have written dy dt. Either way, here is your answer. Whether you wrote dx dt or x prime, that's your call. Suppose you have this. X bar prime is equal to 1, 2, 3. So there's 3 variables. 0, 0, 1 times x plus, say, 0, 1, 3 times e to the t plus 1, 2, 3t. So we're going to add on some t's. There should be x bar. So x bar prime, that means x prime, y prime, z prime, is equal to this times, to save a little space, that times x, y, z, which is 1x plus 2y plus 0z, which I won't write. Second row will be 2 times x plus 1 times y plus 3z. And the last row has 0x's plus 0y's plus 1z plus the function of x, of t's. You have 0t, which I won't write, 0e to the t, excuse me, which is 0, plus 1t. And then you have 1e to the t plus 2t's. And then you have 1z plus 3e to the t plus 3t. Maybe I'll even write that in matrix. And basically the next line, to save some space and also to show you how easy it is to go to the next line, basically all you do is remove the brackets and that equal sign in the middle. We had one bracket, a big bracket, we had an equal. I erased the equal. Now just put 3 equals. X prime equals that, y prime equals that equation, and z prime equals that equation. Straightforward. Okay. Now we're going to verify that something is a solution. I claim that if dx dt is 3x minus 4y and dy dt is 4x minus 7y, then x bar should be the matrix 1, 2 times e to the negative 5t. Now remember that if you have a matrix A times the scalar, that's the same as the scalar times the matrix. So here we have a matrix times the scalar. I can put the scalar in front of the matrix. And another thing is, if you have matrix B and you're multiplying by RA, which is the same as AR, you can multiply B and A first, those two matrices, and then scale it by the R. So we want to verify that that's the solution. The solution to x prime is equal to ax. That's what we want to know. Okay. Now, we know that x prime is little x prime, little y prime. Now, what is x prime? Well, we know that x bar is the matrix 1, 2, e to the negative 5t. That is, it's 1 times that, which is e to the negative 5t, 2 times that. So x bar prime, that is the derivative of each of those, will be negative 5 e to the negative 5t, and negative 10 e to the negative 5t. So that is what x prime bar better be. That is what x prime bar should be. So the question is x prime equal to the matrix times x? The matrix is 3, negative 4, 4, negative 7 times x. Times x bar, excuse me, which is 1, 2, e to the negative 5t. When we talked about this, I can bring that scalar, this scalar, all the way in front. It's e to the negative 5t times 3, negative 4, 4, negative 7 times 1, 2. So there's the e to the negative 5t. This row dotted with that column is 3 minus 8, which is negative 5. And this row dotted with that column is negative 10. But that's exactly what this says. This is negative, this times that, negative 5 e to the negative 5t, negative 10 times that. Which is exactly what we wanted to get for x bar. That is, it did check. It did check. Make sure you understand that. X bar prime is equal to 2, 1, negative 1, 0 times x bar. And they tell us that x bar is 1, 3 e to the t plus 4, negative 4 times t e to the t. Well, what would x bar prime be? Well, the derivative of e to the t is just e to the t. So when you multiply e to the t by 1, you're just going to get 1 times the derivative of e to the t. When you multiply e to the t by 3, the derivative will just be 3 times e to the t. That is, we just get this. Now, what is the derivative of t times e to the t? Let's use the product rule. The derivative of the first, which is 1, times the second, e to the t, plus the first, t, times the derivative of the second, which is e to the t. In fact, we get 1 plus t e to the t. And when you multiply it by those scalars, those constants, you're just going to get a multiple of that. You're going to get 4 times 1 plus t times e to the t. And you're also going to get negative 4 times that. That's the derivative. Now, it turns out that there's some like terms. In fact, maybe it would have been better if we didn't factor. Maybe it would have been better if we didn't factor. I'll explain why in a moment. Because here we have 1 e to the t, and I'm adding 4 more. So I'm going to get 5 e to the t's. Let's not forget plus 4t e to the t. In the bottom I have 3 e to the t, but I'm adding on negative 4 e to the t. So I'll be left with negative 1 e to the t plus negative 4 t e to the t's. So that is x prime bar. Okay, so let's see if this works. So I take 2, 1, negative 1, 0, and I multiply it by x bar, 1, 3 times e to the t, plus 4, negative 4 times t e to the t. Well, when you multiply this first row by that matrix, you get 5 e to the t. Plus, when you multiply those two matrices, you get 12, I guess. You get 4, excuse me. You get 8 minus 4, which is 4, plus 4t e to the t. Exactly this top row. Okay. Now when you multiply this matrix, or that row, by 1, 3, you get negative 1 e to the t. Negative 1 e to the t. You multiply it by that, you get negative 4 times t e to the t, which is exactly what we were supposed to get. It is x bar prime. Okay, that is this, use blue, this matrix times x. This matrix times the given x. It did give us x bar prime. Because I took x bar, I primed it, that is, I took the derivative of it, and I got that answer in the bottom. Exactly what we got. We did get back x bar prime. Now, let's talk about if solutions are fundamental. That means that they're linearly independent. The solutions are linearly independent. So we have x bar prime is equal to a matrix A times x bar. Okay? And suppose two solutions are x1 is equal to 1 negative 1 times e to the t, and x sub 2 is 2, 6 times e to the t. Let's even make it more complicated. Plus 8, negative 8 times t e to the t. So the question is, are x1 and x2 fundamental? That is, do they form a fundamental solution? It's just asking, are they independent? Now, there's no way you can take a linear combination of things that have e to the t's and add on things that have e to the t's plus te to the t's and get 0. The only way you're going to get the te to the t's to be 0 is to take a 0 multiple of x2's. Well, then this whole thing, including the e to the t's, this whole thing will be 0. If you want this to be 0, well then c1x1 better be 0. And since x1 is not 0, then c1 has to be 0. That is, you'd have to take 0x1 plus 0x2 to get 0. It is only the trivial solution, only the trivial linear combination will give you 0. But how can you do that? You can look at the determinant. This is 1e to the t, negative 1e to the t. This is the same as e to the t, negative e to the t. And the next matrix is 2e to the t plus 8t e to the t. 6e to the t minus 8t e to the t. Remember, this is just one value. You calculate the determinant. You multiply those two, which is 6e to the 2t minus 8t e to the 2t minus that product. Well, I'm pretty sure I said it. This product here is negative e to the t. Negative e to the t. Not e to the negative t. Okay. So when you multiply this with that, well, first it'll become plus. And then you get 2e to the 2t plus 8t e to the 2t. And this plus that is not 0. It's 8e to the 2t. And this plus that is 0. Well, the bottom line is you didn't get 0, which implies linearly independent, which implies fundamental solution. Do x1 and x2 form a fundamental solution? The answer is yes. If you don't get 0, the answer is yes. You can find a non-trivial linear combination. A linear combination of x1 and x2 will be some number of x1 plus some number of x2 equals 0. And if it must be, I mean, this statement is always true. You'll always get the 0 vector. You'll always get the 0 vector. Question is, must they be 0? I mean, maybe you can take 3 x1s and add 2 x2s and get 0. If you could, those two vectors x1 and x2 are dependent. Okay. So suppose you have these three solutions. 2, negative 4, 8 plus t times 2, 4, 4, that's x1. X sub 2 is 1, negative 2, 4. And lastly, x sub 3 is equal to, say, 1, negative 2, 4 plus t times 1, 2, 2. Now, we have three vectors. you want to see if you can get the 0 vector when you add multiples of each of the vectors. Of course, the multiples can be just 1. That is, you just add the 3 vectors. Now, if I can come up with, say, this equation. Oops. A non-zero multiple of C1 plus a non-zero multiple of C2, for example, and I get 0. In fact, just one of the C1s have to be non-zero. Well, if C1 and if X1 and X2 are dependent, well then of course I can find a linear combination of all 3 of them. Now it doesn't have to be the linear combination I am going to write, but this one will always work. If you take C1 X1 plus C2 X2, well that's the 0 vector, and then add on 0 X3. The 0 vector plus this is the 0 vector. That will give you the 0 vector. Okay, so I found a non-trivial solution. Non-trivial linear combination. What does that mean? At least one of these is not 0. Of course, it's not that number that's not 0. That number is 0. But one of these are not. So you should really try to do this always. Spend a few seconds to just look at the 3 vectors or the 3 matrices and see if you can see it. Well, I noticed that when you double this vector, you get that vector. If you double that, you'll get 2, -4, 8. Exactly that. And when you double this one, you'll get t times 2, 4, 4. So I know that x1 is 2 times x2. We'll bring that over to the other side. The x1 minus 2x2, that gives you the 0 vector. And after all, if you have 7, 7, 7, and you take away 7, 7, 7, you don't get 0. You get 7 minus 7, 0. You get 7 minus 7, 0. 7 minus 7, 0. Okay, I mean, we could have had 3, 4, 5, and you take away 3, 4, 5. You don't get 0, but rather you get the 0 vector. And you put a bar on top when you want to signify that it's not a number, but it's a vector. Okay. So, bottom right, or the middle right, I have a linear combination of x1 and x2 that give me 0. It's 1x1 minus 2x2, which will equal 0. Now, if you wrote this down, that this vector is 2 times that vector, I wrote that there, teacher can see that you saw that. And you bring this over, you get this equation. So 1x1 minus 2x2 plus 0 times the third vector, that'll give you 0, the 0 vector. And I found the linear combination of x1, x2, and x3. And not all of the coefficients were 0. That's not 0. That's not 0. But yet, the result is the 0 vector. This implies linearly dependent, which implies it's not. That implies x1, x2, and x3 do not form a fundamental solution. Fundamental solution just means that the given solutions are independent. If you're not fundamental, it means the solutions are dependent. Okay, so now we're going to verify that x particular is a solution. Suppose that you come to know that dx dt, or you're given that dx dt is x plus 4y plus 2t minus 7. dy dt is 3x plus 2y minus 4t minus 18. And x sub p is 2 negative 1 times t plus 5, 1. Now, that means that x particular, which is xy, is equal to 2t plus 5, 2t plus 5, and negative t plus 1. Negative t plus 1. Well, that would tell me that the derivative of x sub p, that is x prime y prime, and taking derivative with respect to t, that will be 2, and the derivative of that will be negative 1. Okay, so x sub x particular prime is 2 negative 1. Alright, so let's see if this is right. Now when we write this up in matrix form, x bar prime is supposed to equal to A, which is 1, 4, 3, 2 in the bottom, times x particular, plus the functions of t's. 2t minus 7 plus 2t minus 7, and minus 4t minus 18. So well, actually, we know that's true. Now we want it to know if it's true for our given x. Our given x is 2 negative 1 times t plus 5, 1. Don't forget to add on everything else. All I did from this line to this line was substitute in what x sub p is. That didn't change, and plus that didn't change. Well, 1, 4 times 2 negative 1 is negative 2 times t. This times that, because I can distribute, is 5 plus 4 is 9, plus this, plus 2t minus 7. Well, that's just going to be 2, which is just what we wanted, because that cancels. When I multiply 3, 2 by 2 negative 1, I get 6 minus 2, which is 4 t's. And then when I do that product, I get plus 15 plus 2 is 17. Plus this, that is minus 4t minus 18. Well, 4t minus 4t cancels to 0, and 17 minus 18 is negative 1. Exactly what I wanted, and that is x sub p prime. So it did check. Let's do one more problem. Suppose you know that x prime is 2, 1, 1, negative 1 times x, these are all bars, plus negative 5, 2. I claim that xp is 1, 3. That is, a particular solution is 1, 3. And remember that xp means little x, little y. Little x is 1, little y is 3. The xp bar, or x prime, is the derivative of xp. Well, if x is 1, with respect to t, the derivative is 0. And if y is 3, dy dt will be 0. Okay, so let's see if we get that. So now we have x prime bar, bar goes on the top, is equal to 2, 1, 1, negative 1 times x sub p plus negative 5, 2. And we want to question that equal sign. Well, this times that. 2 times 1 is 2, plus 1 times 3 is 3, 2 plus 3 is 5. This times that. 1 times 1 is 1, negative 1 times 3 is negative 3, 1 plus negative 3 is negative 2. What I just wrote down was just what this equals. Let's not forget to add negative 5, 2, which is 0, 0. It is true. Okay, that completes this introductory section on systems of linear first order differential equations. Do lots of problems, they're not that bad.